let's imagine shining a light through a narrow slit.
Yeah.
What shape would you think the light would make on the wall behind it?
Well, most people would probably guess like a single line
Right.
etching the slit, but that's not what we see. We
Mhm.
get a pattern of bright and dark bands spread out on the wall.
Okay. Interesting.
That's called diffraction, and it tells us that light is acting like a wave.
Like ripples.
Exactly.
Okay, so light's a wave.
Yeah.
But then let's say we add a second slit.
Okay.
What happens now?
Now things get even weirder.
Okay.
Instead of two lines of light, we see a pattern of alternating bright and dark bands.
Huh.
An interference pattern,
Okay.
just like you'd see with water waves,
Right.
overlapping and creating zones of high and low intensity.
I see.
This was huge back in the 1800s because it really solidified the idea that light was a wave.
Yeah, so case closed, right?
Well, not quite.
Oh.
Fast forward to the early 1900s, and the discovery of the photoelectric effect threw a wrench into that neat picture of light as a wave. This showed that light can act as if it's made of individual particles,
Wow.
called photons.
So now it's particles,
Yeah.
but it's also a wave.
So is light a wave or a particle?
Right, that's the question.
That's the paradox.
Yeah.
And this is where the double-slit experiment gets even more fascinating.
Okay.
Imagine we're firing individual electrons,
Okay.
not light this time, one by one, at those two slits.
Okay, I'm picturing it.
You might expect each electron to act like a tiny marble, going through one slit or the other,
Yeah.
and leaving a tiny dot on the screen behind the slits.
Right. Like so.
And at first,
Yeah.
that's what happens.
Okay.
But if you let enough electrons go through,
Mm-hmm.
the same interference pattern emerges,
Really?
as if each electron somehow went through both slits and interfered with itself.
What? So even a single electron
Yeah.
can create that wave-like pattern.
It's mind-boggling, right? This is one of the core principles of quantum mechanics.
Okay.
Particles, like electrons, can exhibit both wave-like and particle-like behavior.
Okay.
It's called wave-particle duality.
Wave-particle duality.
Yeah.
Okay, so how do we even know it goes through both slits? Like, can we not try to watch it go through the slits?
That's a great question, and scientists have actually tried to do just that with what's called a which-way experiment.
Okay.
They try to determine which slit each particle goes through.
Okay.
But here's the thing. The act of observing,
Right.
of trying to measure which path the electron takes,
Yeah.
changes the outcome.
Seriously. So
Yeah.
we can find out which slit it went through,
Yes.
but it changes the experiment.
As soon as you try to observe which path the electron takes, the interference pattern disappears,
Wow.
and it acts solely like a particle. It's as if by observing, we force it to choose a single path, and the wave-like behavior vanishes.
Okay, that's pretty wild.
This is known as the complementarity principle.
Complementarity principle.
Yeah.
Okay.
You can observe either the wave-like or particle-like nature of a quantum object, but you can't observe both at the same time.
So you're saying the act of measuring is influencing the thing you're trying to measure.
That's exactly it.
Yeah.
And it gets even stranger.
Oh, no. Stranger than this.
Oh, yeah. Have you heard of delayed choice experiments?
No, I don't think so.
Okay, so imagine the same double slit setup,
Okay.
but this time we decide whether or not to observe which slit the electron goes through.
Right.
But we make this decision after it's already passed through the slits.
Hold on. So after it's already gone through,
Yes.
you're then deciding whether to measure it or not.
It seems impossible, right?
Yeah.
But that's what these experiments suggest.
Wow.
It's as if the electron somehow knows in advance whether we'll be observing its path and chooses to behave accordingly, even though the choice to observe is made later.
Okay, so does that mean the future can influence the past?
That's a question that physicists and philosophers are still grappling with.
Yeah, I bet.
The delayed choice experiment throws into question our everyday notions of cause and effect,
Right.
suggesting that at the quantum level, things might not be so clear-cut.
It's pretty mind-blowing.
It really is.
Okay, so we've got this wave-particle duality,
Yes.
and it's weirder than we could have imagined.
It really challenges our understanding of reality.
Yeah.
But how do scientists try to make sense of all of this?
Right. Let's talk about that.
Yeah, it's a lot to wrap your head around.
It really is. So we've got all this quantum weirdness going on, but why don't we see these quantum effects all around us?
Right, like why does a chair just look like a chair?
Yeah, why does the world seem so normal?
That's where this idea of decoherence comes in.
Decoherence, okay?
You see, in the quantum world, things can exist in multiple states at once.
Okay.
But in the macroscopic world, the world we experience,
Yeah.
objects have definite properties. Decoherence is the process by which quantum systems lose their coherence
Okay.
or their wave-like properties
I see.
due to interactions with the environment.
So it's like the environment is constantly measuring everything.
That's a good analogy. Think of it like this.
Okay.
An electron in a vacuum.
Okay.
It can show those wave-like properties going through both slits,
Right.
but in the real world,
Yeah.
that electron's never truly isolated. It's
Yeah.
constantly bumping into air molecules, photons,
Okay.
other particles.
Yeah.
These interactions essentially act as measurements,
I see.
causing the electron's wave function to collapse
Okay.
and forcing it to behave like a particle.
So the bigger the object,
Yes,
the more it interacts with its surroundings,
exactly.
and the less we see that quantum weirdness.
That's the idea. A baseball, for instance,
Okay.
it's made up of trillions and trillions of atoms
Right.
all interacting with each other and the environment.
Okay.
So any quantum coherence is washed out.
Makes sense.
And the baseball just behaves like, well,
Yeah.
a baseball.
So it's like there's this hidden quantum world,
Right, it's all around us.
and it has all these strange rules,
Yeah,
but as things get bigger,
yeah.
those rules get hidden by the classical world.
Exactly. It's like two sets of rules.
Hmm.
But even though we don't see it directly,
Yeah.
the quantum world is still shaping our world.
Right.
Think about technology. Lasers, transistors, MRI machines.
Yeah.
Those wouldn't exist without quantum mechanics.
So even if I don't see an electron going through two slits at once,
Exactly.
quantum mechanics is still affecting my life.
Absolutely. Like, it's really fascinating, right?
Yeah, it is. So let's talk a bit more about those interpretations.
Okay. Which ones are you thinking about?
Well, like the Copenhagen interpretation
Right.
and the many worlds interpretation.
Okay, good choices.
What are the main differences there?
So the Copenhagen interpretation says the wave function collapses when a measurement's made.
Okay.
It's very pragmatic. It focuses on predicting outcomes, and it does it really well.
Okay.
But it doesn't actually say what's happening during that collapse.
Right. So it just says what we see.
It's a bit like saying, this is what we observe, but we don't know exactly why.
Right. So it's almost like a black box.
Yeah, you could say that.
Okay. So then what about the many worlds interpretation?
The many worlds interpretation, it's much bolder.
Okay.
It says there's no collapse at all.
Oh.
Just a continuous branching of the universe.
Whoa. Branching.
Yeah, so every possible outcome of a measurement
Right.
actually occurs, but in a different branch.
A different branch of the universe.
exactly said.
So every time something happens, the universe splits.
A radical idea, right?
Yeah. Very radical.
Uh-huh.
So there would be like infinite universes.
That's the implication.
Wow.
And that's why it's so controversial. It's tough to wrap our minds around
Yeah, I can imagine.
an infinite multiverse.
Mhm.
And it's also hard to test experimentally.
Right. How do you even begin to test that?
Yeah, it's a challenge.
Okay, so Copenhagen says the wave function collapses,
Right.
and many worlds says the universe splits,
Yeah.
and there's no collapse. What about that pilot wave theory?
Yes, the pilot wave theory.
It's deterministic, right?
Exactly.
So no randomness.
In the pilot wave theory, everything's predetermined.
Interesting.
It says the particle's trajectory
Mm-hmm.
is set from the start,
Okay.
guided by this pilot wave.
Guided, okay.
And the interference pattern comes from the particle interacting with this wave.
So the particle itself still only goes through one slit,
Right.
but it's guided by this wave that goes through both,
That's the basic idea. Some physicists find it very appealing.
because it's more predictable.
Yes, it removes the randomness from quantum mechanics.
Right, so it's closer to how we normally think about the world.
Exactly.
Yeah.
But it also has its issues.
Like what?
Well, it introduces this concept of a quantum potential
Okay.
that guides the particle.
Yeah.
And this potential can act non-locally.
Non-locally. What does that mean?
It means it can affect the particle instantly,
Instantly.
regardless of distance.
So faster than light.
Yeah, that's the problem. It clashes with Einstein's relativity.
So another challenge.
It highlights the fact that we're still searching for a complete picture of quantum mechanics.
Right, so we've got these three interpretations,
At least.
and they all have their pros and cons.
Yeah,
Is there any way to know which one is right?
that is the million-dollar question.
Yeah.
right now there's no way to definitively test these against each other.
Okay.
They all make the same predictions.
So how do we choose?
It's a bit of a philosophical debate at this point,
Mm.
but that doesn't mean the search is over.
Right.
Physicists are developing new experiments all the time,
That makes sense.
pushing the boundaries of what we know.
Yeah. I hope someday they figure it out.
It's an exciting field to be in.
It really is. So we've talked a lot about the theory,
Yeah.
but what about real-world applications?
That's a good question, because it shows that quantum mechanics isn't just theoretical.
Right.
It has practical implications, too.
So like what kind of applications?
Well, for one, there's quantum computing.
Okay, I've heard of that.
Quantum computers use superposition and entanglement
Yeah.
to do calculations that normal computers can't.
Hmm.
They could revolutionize things.
Like what?
Drug discovery, materials science, AI.
Wow, that's amazing.
There's a whole new way of computing.
So we're not just understanding the universe better,
Right.
but we're using that understanding to build new things.
Exactly, like quantum cryptography.
Okay, what's that?
It uses quantum mechanics to make unbreakable encryption,
Unbreakable. Wow.
so we can have secure communication.
That's really important.
And there's also quantum dots,
Quantum dots, okay.
tiny semiconductor nanocrystals.
Okay.
They have quantum properties,
Uh-huh.
and they're used in all sorts of things.
Like what kinds of things?
Displays, lighting, medical imaging, even solar cells.
So it's like we're surrounded by quantum technology.
In a way, yes. It's pretty incredible, right?
It is. It's amazing how something so strange
Yeah.
can have such a big impact on our lives.
It shows that the quantum world is more than just a curiosity.
Right.
It's a fundamental part of nature.
And it's affecting our world in ways we might not even realize.
Absolutely.
It really makes you think, right?
It does. The Double-Slit Experiment really highlights how much we still don't know.
Yeah. And how weird the universe can be.
Exactly.
So we've talked about how wave-particle duality is kind of this fundamental thing in the quantum world.
Yeah.
But how far does it go? Like, does it apply to everything?
That's a great question.
Yeah.
And scientists have been trying to figure that out.
Mm.
They've been pushing the limits of the Double-Slit Experiment,
Yeah.
trying to see if they can observe interference patterns
Right.
with larger and larger objects.
And have they been able to?
They have, actually, and it's pretty remarkable.
Yeah.
They've done it with molecules that have hundreds or even thousands of atoms.
Thousands of atoms.
Yeah, it's mind-boggling, right?
That's crazy. So, like, the quantum world is almost becoming macroscopic.
In a way, yes. And it raises the question of
Yeah.
whether wave-particle duality might apply to everything.
So, like, could you, theoretically, do the experiment with a baseball?
Theoretically.
Yeah.
Yeah, the math of quantum mechanics doesn't really care about size. It suggests that any object could have wave-like properties.
Okay, but then why don't we see baseballs diffracting?
That's where it gets tricky for a big object like a baseball.
Yeah.
The wavelength associated with its motion is just incredibly tiny,
Okay.
like way smaller than the baseball itself.
So the interference pattern would be too small to see?
Yeah, it would be practically impossible to detect.
Hmm.
It'd be like trying to find a specific grain of sand on a beach.
Yeah, I get it. So even though we can't see it,
Right.
the principle still applies.
That's the current thinking, yeah. It's
Yeah.
pretty wild to think about.
It's almost like our everyday world
Yeah.
is just this tiny sliver of a much bigger, weirder reality.
It really puts things into perspective.
It does. This whole deep dive has been really eye-opening.
It's been a pleasure talking about this with you.
I feel like we've just scratched the surface, though.
There's always more to learn, especially in quantum mechanics.
So, to our listeners out there,
Yeah.
the double-slit experiment shows us that the universe is full of surprises.
Absolutely.
What else might be out there? What other impossible things might actually be true?
It's a great question to ponder.
Keep exploring, keep questioning, and who knows what you might discover.